Last time we learned what the tangent space is and what vector fields are. And today we want to talk about tensor fields. And we do this step by step. So the next step we need is to introduce a cotangent space and covector fields. And then from vector fields and covector fields, we build tensor fields of arbitrarily high rank. So that will be the program for the next 40 minutes or so. Let me just remind you of a few things. So we had the tangent space TPM. This was constructed as a set of derivations, which might look a little bit abstract at first sight, but you will see that it is quite useful for calculations. Then we discussed vector fields. So these were maps which assign to each foot point a point in the tangent space at this point, and we usually write them with respect to the standard basis d mu, which is just a shorthand for d by dx mu. So these are fields of derivations. So these are particular vector fields. Now these are operators which act on functions, and that's the way in which we had defined vector fields on a manifold. And the last thing we did was that we calculated the transformation behavior of these x mu's. So if we write this also with the second basis, so this here is a shorthand, of course, for d by dx twiddle mu. Yeah, so I put the twiddle over the derivative. Where else should I put it? So then we calculated how these two things are related to each other, and we found that this is given by the Jacobi matrix of the transformation. So J mu mu was the Jacobi matrix dx mu twiddle by dx mu. So the components of a vector field transform with the Jacobi matrix of the change of coordinates. And I already told you that many books, in particular older books, use this as a definition of a vector field. So they say a vector field is a thing which is characterized by a quantity with one upper index. And this transforms if I change the coordinates according to this law. That's what they use as a definition of a vector field. I prefer to do it in a more geometric way, which you will find in most modern books on differential geometry, but this is perfectly equivalent. So that was the last thing we did. And now we want to introduce the cotangent space. So to every vector space, we can define what is called the dual space. And we will introduce a cotangent space as a dual space of TPM. So I first remind you, I guess that most of you have seen this before, I remind you what the dual space of a vector space is. So this makes sense for any vector space. Well, to be on the safe side, let's say finite dimensional vector space. So for any finite dimensional vector space. You know, in quantum mechanics, for instance, we deal with infinite dimensional vector spaces, and then there's a little bit care should be used when you deal with a dual space, because usually you also require some sort of continuity. That's not necessary for finite dimensional vector space. For any finite dimensional vector space, V. So we will later apply this to the case that V is TPM. We define the dual space, the dual vector space, which is usually denoted by a star, as the set of all linear maps from V to R. Yeah? So if I have a vector space, then I can consider maps from V into R, and I require them to be linear, which makes sense if V is a vector space. And what I get is obviously again a vector space. So such maps can be added together, and they can be multiplied with numbers. And actually it's a vector space of the same dimension. That's what we call the dual space. And what we are interested in is the dual space of this TPM. So the dual space of TPM is, well, it would be denoted TPM. And if I put the star here, then you could be confused because it would look like the star would be associated with the M. So that's the reason why one usually puts the star here. Yeah, that's the usual notation which you find in more or less any book on differential geometry. And this is called the cotangent space. So an element of TPM star is a map from TPM into R. If I have an alpha and it is situated at a particular point, that's the reason why I put an index P here, is a map. Alpha P goes from TPM to R. So it makes vectors into numbers. Yeah, as the English usually say, it eats vectors and it gives you numbers. Okay, so that's a dual space. Now you might think, okay, I have learned how to make one vector space into another one. Let's do this several times. Maybe we get interesting new things. So you could consider the dual of the dual, and then the dual of the dual of the dual, and so on. And you might hope that you get something more and more interesting if you proceed. But that's not the case. Actually, you get absolutely nothing new. If you consider the bidual, you come back to your original vector space. So let me write this as a remark. So you can do this only once. Then from then onwards, you don't get anything new. Note that's a bidual. So I would write this now in this way with a bracket around TP star M. Is identical with TPM. And how does this work? So it works by identifying a point XP in TPM with something which lives in this space. So it is to be identified with something, let's call it XP hat. And then I want to identify XP with XP hat. And this should be an element of this space, should go from TPM star into R. Now if I have a vector, I can easily construct such a map. Namely, every covector alpha p is just applied to this XP. Yeah? If you give me the XP, this map is well defined. I can associate any alpha p with this number. This gives me a linear map from TPM star to R, so it gives me an element of this space. And obviously it is uniquely determined by the XP. And if you play a little bit around, you will see that it's also the other way around. So it's not only injective, it's a bijective map. So I can use this for identifying TPM with its bidual. So the bidual is nothing new. That's the reason why we usually don't use this symbol. We just write TPM and we identify the two things. Yeah? So that's what we can make with the help of the dual operation. So this gives us the covector fields. And the same game we played with the tangent spaces, now we can also play with the cotangent spaces. We can consider something which we call the cotangent bundle. Remember, the union of all these things we call the tangent bundle. This was the union of all the tangent spaces sitting at any point in the manifold M. And we define quite analogously now the union of all the TPM, where the unification is done over the foot point, is called the cotangent bundle. Over M. Cotangent vectors are not so easy to visualize. Usually we visualize tangent vectors by arrows. Yeah? Well, a covector is something which is applied, where is it written here, which is applied to vectors and then gives a real number. So that's not so easy to visualize. One way of visualizing it, you could depict the kernel of the map, the vectors which are mapped onto 0. this would give you a hyperplane. So you could visualize any covector as a hyperplane, meaning the hyperplane on which the covector vanishes, the map vanishes. So you might think of a covector field as something which maps into the cotangent bundle as something which assigns a hyperplane to each point. But this doesn't give the full information because the kernel doesn't tell you, doesn't give you the map completely, right? If two covectors are multiples of each other, then they have the same kernel, but they are of course not the same covector. So it doesn't give the full information. So cotangent vectors are a little bit difficult to visualize, but yeah, they are just defined as maps. Okay. Yeah, and I haven't written this yet. I have written what the cotangent bundle is, and then of course a covector field. Yeah, we had vector fields as maps which assign to each foot point a vector at this point. And a covector field, surprise, is now something which assigns a covector to a covector field is a map from M. Oh, I forgot to write the symbol here. We abbreviate this by T star n. Yeah, we write T star n for this quantity. So a covector field is a map from M into T star n that assigns to each P in M a covector alpha P, which is at this point. So it is in T Pm star. Yeah, if I just give you this here, if I say it's a map from M to T star M, that wouldn't be the full information, because it could be a map which assigns to this point P a covector which is attached to quite a different point, right? So it's really meant in the way that the covector is at the point at which I evaluate this map. So it's, well, if some of you have some familiarity with bundle theory, then you would realize that that's what we call a section in the bundle. But I don't want to use a bundle language here, because it's actually not needed. Okay, so that's the definition of the cotangent bundle. And now we can construct cotangent vectors in one interesting way. Namely, if we have a function, every function f, I denoted them in this way. Yeah, so these were the C infinity maps from M to R. So that's what we usually just call functions on the manifold, real valued functions on the manifold. And I claim that any functions defines a covector field which is denoted df. That's a precise mathematical notion. It's not what what physicists sometimes use as intuitive thing of something which is infinitesimally small or things like that. That's a well-defined operator, which is called the exterior derivative, and I will tell you what it does to the function f. So df is a precise mathematical object. It's a covector field. So I have to tell you what is df at a point p. Yeah, I want to tell you what this covector field is. So I have to tell you what does it at a point P, and this is supposed to be a map from TPM to R. So I have to tell you what does it do to a vector xp, and what it does is it applies xp, which is a derivation to the function f. That's well defined, right? For any xp, I can calculate this thing. I can apply the operator xp to my function f. This gives me a real number at each fixed point p. So I get, for each p, I get such a covector, and if I let the point p float over the manifold, then I get a covector field. And that's what we call the differential of f. It's a well-defined object. It's defined by applying vector fields in the usual way, in the sense of a derivative to my function f. So define the covector field here, blah, 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 and df is called the differential of f. Hope we can read this. Okay, so for this reason, covector fields are also sometimes called differential one forms. Maybe it occasionally happens that I use the word one form instead of covector field. Actually, I want to try to avoid this word because I think it's already vocabulary enough. But sometimes it might slip. I might just use this word. So if I use the word one form, that's just another word for covector field, and it comes from this property that the differential is a particular covector field, and for this reason one speaks of differential one forms. Okay, so that's the definition of the df, and now we can calculate the transformation behavior of covector fields under coordinate changes. So we have here calculated the transformation behavior of vector fields. Now we do the same thing for covector fields. And maybe then you get an idea what these funny index rules, some indices up and some indices down, what's the idea behind this. Because then we will, for the first time, see the different transformation behavior of lower indices and upper indices. Okay, so I want now to look at covector fields in a chart. So in the chart, well, hope everybody remembers what the chart was. We had it introduced as a map from the set U to O, and U was an open subset in my manifold, and O was an open subset in Rn. So it was what is usually called just a grid of coordinates. Yeah, it assigns a grid of coordinates to my manifold, or rather to a subset U. So if I have a point P here, I get phi of P, which is an n-tuple. So one usually writes it as x1 of P to xn of P. And now these x1 to xn, these x mu's, they are real valued function, right? This is an n-tuple of real numbers, so each entry is a real number. So the x mu is a map from U to the reals. So it's a map like this F here. Well, it's not defined on all of M, but on the subset U. We have at each P and U the basis for the vector space Tp star M constructed in the following way. I apply this operator D to x1 and evaluate this x at the point P. x1 is a real valued function. I can apply the derivative operator, so I get a one form, and I evaluate this at the point P. And I do this for all n functions. And this gives me, in fact, so it's obvious that it gives me n covector fields. What you have to check is that they are really linearly independent. But I think the geometric idea is quite clear, because a coordinate system is something where the coordinate lines never become tangent. And that's a tangent to each other. So two different coordinate lines can never be tangent to each other. And that's the reason why this is a basis. So I think I can skip a formal proof. So I think this is geometrically quite intuitive that they form a basis. And then we can write any covector field alpha, well, not on all of M, but at least on U, where my chart is defined. Write any covector field M as a linear combination, as a linear combination of these dx mu's. And the coefficients, they are real numbers, well, at each point. So if the point is floating over U, then this gives a real valued function. So these coefficients are denoted alpha mu. And now you see they must have a lower index, because here's an upper index. If I want to form a sum, if I want to be in agreement with the summation convention, then the index must be a lower index. And we will now see that this results in a different transformation behavior for these things as for the x's, which have an upper index. So we want to calculate transformation behavior of the components. Yeah, that's what we call the components of the covector field in this coordinate system. behavior of the components alpha mu under change of coordinates. So we want to do the same calculation we did last time for the vector fields, now for the covector fields. So we write our alpha as alpha mu dx mu, and in another chart we write it as alpha nu twiddle dx mu twiddle. And we want to know how are these two things related. And of course we need to know how the basis covectors are related to each other, but that's obvious. As a d is defined just as a usual derivation. Yeah, it's defined by applying a derivative operator, and this derivative operator satisfies the usual chain rules and product rules and so on. We can just calculate this with the chain rule. So this represents the news basis covector in the twiddled coordinates as a linear combination of the basis covectors in the untwiddled coordinates. And the coefficients which appear are just the elements of the Jacobi matrix. So that's exactly what we abbreviated in this way. So we have the same object which appeared in the transformation behavior of the vector fields. And now we have alpha, so I insert the second equation into the first, so I have dx mu I should have done it the other way around. It's not. I can call this index mu or nu, whatever you like. You just should not have an index more than twice in one formula, right? But summation index can be called as I like. Then I can, no, I have a nu here, sorry. That was a good idea to call it nu. Then I can directly read it from this expression, right? So I insert now this dx mu tilde here. So I get alpha nu tilde, and then comes the Jacobi matrix, j mu mu dx mu. And now I can compare coefficients. Yeah, this is a basis. So if I represent an object of my vector space in a basis, then the coefficients are unique. So I can compare them. This must be the same as this. So I get alpha mu must be j mu alpha mu tilde. Or if I want to solve for the twiddled ones, so then you see, then I have to invert this matrix. So now the inverse Jacobi matrix occurs. J mu nu, oh that's, oh sorry. Let me see. I have an alpha mu here, so I would need mu and mu here. So if you compare this, you see here was a transformation behavior of the vector fields. So you say the twiddled, you see the twiddled coordinates, the twiddled components are given by in terms of the untwiddled ones with the Jacobi matrix. And here it is the inverse Jacobi matrix. And that's a general rule. Every upper index transforms with the Jacobi matrix, and every lower index transforms with the inverse Jacobi matrix. That's the way in which the formalism is done. So otherwise the things would not fit nicely together. So that's the transformation behavior of covector fields, which we have derived in this way just from the product rule and the chain rule. Okay. So now we can go one step further. We can go from vector and covector fields to tensor fields of higher rank. And just as a construction of the co-vector space by means of the dual was a standard construction which you can do with any vector space. Also the formation of tensor products is something you can do with any vector space. So again, I do it in the beginning for an arbitrary vector space V, and then we apply it to TPN. So now we want to define tensors of higher rank. So actually vectors and covectors are special cases of tensors. That's why I say tensors of higher rank. So the lowest rank tensors we already have defined actually, of higher rank. So this goes in the following way. So for any two, and again, to be on the safe side, let's say finite dimensional. For any two finite dimensional vector spaces, spaces V, W, say, one defines the tensor product this is denoted by a cross with a circle around it. So do not confuse the cross with a circle with a cross without a circle. The cross without a circle would just, it's just a set theoretical notion. It would mean the set of all pairs, right? That is denoted by a cross without a circle. That's a Cartesian set product. That's not what is meant here. That's a so-called tensor product, and it's denoted with a circle around the product sign. Defines a tensor product, and it's defined as a set. Oh, now I have to continue up there. Oops. Of all bilinear, it has two entries, so that's why bilinear means linear in each entry. Of all bilinear maps from V star cross W star into R. So it's a map which has two slots, two entries. In the first slot I put an element from V star, and the second from W star, and what it gives me is a real number, and the mapping should be linear in each entry. That's what is meant by bilinear. That's the way in which the tensor product is defined. So that's a tensor product of the spaces. Yeah, so here's this funny sign, the cross with a ring is between two spaces. Now I introduce something where we have the same sign, but now it's between elements. So that's a tensor product of two elements, which I now define. Then for any V in V and little w in the space capital W, we define something which is denoted in this way. So it's a tensor product of the two elements, and this is supposed to be an element of the tensor W. So it should do what? It should be a map of this sort. So it should be a map of this sort. So if you give me a one form alpha from the dual space of V, and the one form beta from the dual space of W, then it should give you a real number. Well, that's easy. Obviously I pair the alpha with a V and I pair the beta with a W. So I apply alpha, no, the other, yeah, it was okay. Alpha to V and beta to W. Yeah? This is a covector, so it eats vectors, gives a real number. This is also a covector, so it eats vectors, gives a real number. And these two real numbers can be multiplied together. And that's what the tensor product is. So with this construction, it's fairly easy to show that the tensor product is again a vector space, and that the dimension is a product of the dimension of the individual spaces. Namely, you can build a basis out of a basis on V and a basis of W just by using tensor products. So it's not difficult to show, but it's boring, so I don't want to waste any time on this. So I just tell you V W is a vector space, that's obvious. Yeah? That you can add such maps together and that you can multiply them with real numbers, and that's the usual rules hold. That's obvious. But what's the dimension of the spaces? That's not quite so obvious, but it's not really difficult. It's a vector space. So what you find is that the dimension is the product of the dimensions of V and W. And the way in which you prove it is that you choose a basis for V and you choose a basis for W, and then you prove that the tensor product of these two bases is a basis for the bigger space. And then, well, you have, if this is n-dimensional, you have n basis vectors here. If this is m-dimensional, you have m basis vectors here. And if you multiply them pairwise together, you get n times m basis vectors for the whole space, right? So I leave it with this, but if you want to prove this, I think you could fairly easily do this by yourself with the help of basis. So yeah, we can do this with any two vector spaces. So, and we can just do as often as we like. So if we have this vector space, then we can form the vector as a tensor product with an even bigger vector space. And we can do this iteratively. And that's the way in which tensor spaces over a manifold are constructed. Namely, we multiply, in the sense of the tensor product, TPM and TP star together as often as we like. And then we get tensor spaces of arbitrarily high rank. So that's the definition of the tensor spaces over a manifold. So how do I want to denote this? Yeah. In this notation, we define the tensor space of rank R, S over the manifold M at a point P in M as what? So this is usually denoted in this way. It has two indices, RS, that's the two numbers which give the rank. I am at the point P, so I put this as a foot point and then the M. And it's defined as what? I have R times TPM multiplied together in the sense of the tensor product, and S times the dual space. So I have TPM tensor TPM, and I have, oops, yeah, was okay. Same thing with the star, so here I have R factors, this occurs R times, and this occurs S times. So that's the way in which the tensor space is defined, and you can do this for any R and for any S, right? So in English one usually says tensors of a certain rank. In German one says Stufe instead of rank. Here we speak of Tensorfelder der Stufe R, S in German. But in English the common word is rank. Sometimes you also find degree, but rank is more common. So in particular, we see now that what we have learned before, that the functions, the scalar fields, that's a vector, no, not fields, that's the functions, I'm at a point, that just the scalars, the vectors and the covectors, that they are special cases of this. So you see, what is T naught naught? Well, in a sense, this is a convention, yeah? If I have no factor here, so what do I mean by that? Well, these are maps which go into R, and the usual convention is that I then identify it with the image space. So I identify this just with the real numbers. So this you could say is a convention, that you say, I just want to include the case that I have two zeros here, and then I say it's just R. But what is this here? That's not a convention, it's clear what it is. So here I have 1 times this factor TPM and no other factors else. So I have just TPM. Yeah? So this is the same as TPM. So vectors are tensors of rank 1, 0. Yeah, that's the same thing. A vector is just a different word for a tensor of rank 1, 0. And if I do it the other way around, with the 0 upstairs and the 1 downstairs, then I have here nothing, 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 and then one factor TPM star. So this is just TPM star. So an O1 tensor is just another word for a covector. So the notion of a tensor generalizes the notion of vectors and covectors. Well, the word tensor is actually a funny word, right? It has something to do with tension and something like that. You might wonder where is this funny word coming from? Actually, it comes from physics. Because the first higher ranked tensor which ever occurred in science was the one which was associated with tensions in an elastic body. And people tried to describe an elastic body, the behavior of the elastic body. They had to introduce something like that. It was a tensor which needed two indices, where you had, well, usually one writes it as an O2 tensor, yeah? With 0 here and 2 here. So it is a second ranked tensor. And that's what we nowadays call the, what's the English word? Spannungstensor in German. Stress tensor. Stress tensor is the word. So you see it comes from, historically, it comes from elastic bodies, tensions in elastic bodies. But of course, the theory to which we will apply this has nothing to do with elastic bodies. So the word tensor is actually a historic curiosity. So it's just a multilinear map. That's what it is. Okay, so these are the tensor spaces of higher rank. And now, of course, we can construct the tensor bundles. So now it's just automatic what we are doing, right? So we now define the union over all foot points for any of these tensor spaces. And, well, guess what? We denote this, of course, then by PRSM without the foot point P. And this is called the bundle of tensors of rank R, S over M. So this can be done for arbitrarily large RS. And actually in physics, in relativity in particular, it's not uncommon that we have tensors of rank at least 4. Yeah? So the thing with 4 indices will occur very soon, I think even today. When we speak about curvature, then we will meet a tensor where R plus S is 4. So it has altogether 4 entries. So don't think that just the one with 1 entries and maybe 2 entries are all you need in physics. In some parts of physics you need higher rank tensors. Well, more than 4, the tensor with rank more than 4 is allerdings is actually quite rare. At the moment I don't know any. Does anybody know an example? In physics, I mean. Okay, but fourth rank is common. This occurs frequently. Well, of course, derivatives of covariant derivatives of the fourth rank tensors, they of course have a larger number of indices. But as a basic quantity, I think 4 is the highest which we will encounter. Just to give me an idea, may I ask you, is there anybody who sees this symbol for the first time in his life? So you all have seen it before. It occurred in some basic lectures. Yeah? So I think it's not everywhere in the mathematical introductory courses for physicists that you encounter tensor products. Actually, when I was a student, I had a 4-year course in mathematics at the beginning of my studies, and they never mentioned something like tensor products. Okay, of course you can do a lot of things with tensors. You can study the algebra of tensors in great detail. There are fat books on this. So that's what is called multilinear algebra. That's an algebraic theory of tensors of arbitrarily high rank. I will not do this. I will mention just very few things. And then turn to the more interesting question of how to differentiate tensor fields. But a little bit about the algebraic things have to be said. What do I have here? Yes, I should mention another word. So I said this is tensors of rank r, s. Sometimes you will find the formulation that people say it is s times covariant and r times contravariant. Yeah, so the lower indices are referred to as covariant indices and the upper ones as contravariant indices. This refers, of course, to the transformation behavior. Everyone says, well, for some strange reason, one calls the transformation behavior with the inverse Jacobi matrix covariant, and the one with the Jacobi matrix itself contravariant. So that's a terminology which has become common in the course of time. So if you hear something about contravariant or covariant tensors, this just refers to the position of the indices. And I think I don't show you in detail the calculation how the components of a tensor field transform. I haven't said what a tensor field is. I have just defined the bundle. So a tensor field, I should of course write this down, although probably everybody had guessed it already. A tensor field of rank r, s is the map from M into the RS tensor bundle such that, or just that without such, that is size to each P and M a tensor in PRS P in M. So it's situated at the same point. So it's what in this somewhat sophisticated language is called a section in the tensor bundle. That's the tensor field. And now we can represent tensor fields in terms of basis as we have done it for the vector fields and the covector fields already. So in a local chart, a tensor field of rank r, s is what? Well, it's a linear combination of these basis vector fields, and I need this r times, so I need a subindex now. I have r basis vectors of this type. Here the index runs from mu1 to mu r, and then I need for the s entries here, I need another index, say mu1, that's a tensor product dx mu s. And then I have coefficients, which I call the components of the tensor field. Yeah, so these are the basis vectors in this higher rank tensor space. So I need as many basis vectors as the number r gives me, and I need as many basis covectors as the number s gives me. And then I have coefficients here. So mu1 to mu r, mu1 to mu r, and mu1 to mu s. And as we later will introduce rules of how to shift indices up and down, I'm careful with not writing indices one over the other. I will try never to do this, never to write one index over another, because then you are in confusion when you start shifting indices up and down. And you don't know to which position you have to shift it. So that would be the representation of a tensor field A. Rank S is represented as. So I hope everybody recognizes vector fields and tensor fields as special cases, right? These are the cases where I have only one basis vector here, not a big tensor product. So a vector field would be one where I had only this first vector and nothing else, and then the A has only one upper index, one mu, and no mu's. And a covector would be something where I have only one of these things here and no other basis vectors. And for this I would need one lower index, mu, and nothing else. So these are special cases. That generalizes the setting to arbitrarily high rank. And now we could ask ourselves, how do these things transform under change of coordinates? And I hope you allow me to skip the details of the calculation, because they are a little bit boring, and I think it's quite obvious now. Even without doing the calculation, you should be able to guess what happens, because we have calculated how these things transform. So this obviously implies that every upper index must transform with the Jacobi matrix, and every lower index must transform with the inverse Jacobi matrix. So you can immediately deduce this from the calculation up there. So the transformation behavior of the components is the following. I just write it down without proving it. So, oh my goodness, that's awful. So I want to know what is this thing here with now new indices rho 1 to rho r, say sigma 1 to sigma s. And I want to know how is this related to my old ones, to a mu 1 to mu r, mu 1 to mu s. And the rule is any upper index transforms with j and any lower index with j inverse. So I need r times the Jacobi matrix j. So this goes from mu1 to mu r. And here from rho 1 to rho r. I just said that I don't want to write indices directly above each other, so I should not do it. So I have mu1, mu r. So these are the upper indices, and the lower indices, they transform with a here dot, of course. They are factors in between. They go with J inverse. The inverse Jacobi matrix. And here I need upper indices mu and lower indices sigma. Sigma 1 to sigma s. So that's the transformation behavior. So I think it's obvious what you have to do. Here you just insert the transformation behavior for each of these basis vectors or covectors, which we have calculated before. And then you make you compare the coefficients, yeah, in the twiddled and in the untwiddled coordinates, and then you get this formula. So that's the transformation behavior of tensors of higher rank. So if you look in an older book, they don't tell you anything about tensor products, these funny signs, this cross with a ring or things like that. They just write this line. And they say that defines a tensor field of rank Rs, period. Yeah? So they think just in terms of the components. So they just give you this, this array of numbers and say that characterizes the tensor of rank Rs. And the fact that it really is a tensor that has a correct transformation behavior is given by this line. So from this point of view, the only thing you need to know is this line. Okay. Oops. So what next? Yeah, okay. I should make a remark on what is a C-infinity tensor field. So what does it mean that a tensor field is differentiable? Yeah, I just talk about C-infinity, infinitely often continuously differentiable. The easiest way of defining this is by saying that in any chart, the components are infinitely often differentiable. You can define it in a more sophisticated way by looking at this definition and realizing that this thing is actually a manifold. And then you could say, then you know what it means that the map from M into this manifold is differentiable. We have already defined it. So the two definitions actually coincide. So I write the simpler one. The simpler one is a tensor field is called the C infinity tensor field. If its components, so these are these numbers, a, mu1 to mu r, u1 to mu s. So these are just real valued functions on the set u where the chart is defined, right? These are the coefficients in this linear combination here. So these are just numbers at every point. So if I let the point float, they are functions on n, on a subset on n of n. Components are the infinity functions in any chart. So this tells us what it means that a tensor field is differentiable. But as I said, a somewhat more systematic way would be to realize that this is a manifold, and then to say, well, it's a C infinity tensor field, of course, if this is a C infinity map. We have already defined what it means to be a C infinity map from one manifold into another one, right? But it turns out to be equivalent to this. And that's, of course, for practical purposes easier. Yeah, what sort of algebraic operations can we do with tensor fields? I said I will cut this short. I will not talk too long about this. So 3 algebraic operations are defined for tensor fields. Namely, you can form the sum of two tensors or two tensor fields. Actually, these are algebraic operations, so I can do them pointwise. Yeah? So it doesn't make any difference if I talk about doing the operation for the tensor fields or if I just do the operation pointwise at any one point. So for algebraic operations, this makes no difference. If I have differentiations and things like that in the game, of course, it does make a difference. Or rather, it doesn't make any sense to do this pointwise. For differentiation, I need to have tensor fields defined on a certain neighborhood. Sum of two tensor fields. So I say I can add together two tensor fields, but not arbitrary tensor fields. They must have the same rank. So if I write this in coordinates, then I would have something of this sort. I have something with coordinates with R upper indices and S lower indices, and I can add this to another tensor field if it has the same rank. So it has the same number of upper indices and the same number of lower indices. U1 nonsense. UR, U1, US. And this gives a new tensor field, which of course again has the same number of indices. So that's a rather trivial operation. Slightly less trivial is tensor product. Of tensor fields of arbitrary rank. So they need not be equal. So I have tensor UR, U1, US. And then I have a second one, which may have a different number of upper and lower indices. So say this goes only from sigma 1 to sigma, what else? Sigma t, t is not good. Say r hat. R hat. And here I have tau 1 to tau s hat. And I multiply them together. Well, the components are multiplied together just pointwise in the usual sense. They are real numbers at each point, so I can multiply them. And this gives, in fact, what is the tensor product of A and B. So this here I should have written this also in index-free notation. So this would be written in this way. That one says the tensor A and the tensor B together gives the tensor C. What we construct here is the tensor A and the tensor B together multiplied in the sense of the tensor product, give a new one, say D. And this D has all these indices combined now. UR1 to UR, sigma 1, sigma R hat, U1, US, tau 1, tau S hat. So you see the rank of this tensor is the rank of D is, how do I write this? I write it this way. Yeah, is R plus R hat S plus S hat, right? If Rs and R hat S hat are the ranks of A and B. You just calculate and you just count the indices, right? And the third operation is what is called contraction. Namely, I can do the following. Contraction of a tensor field. Well, it must have at least one upper and one lower index, otherwise it couldn't construct anything. Tensor field of rank Rs with R bigger or equal than 0 and S bigger or equal than 0. And that's defined in the following way. I just equate two indices. This means I sum over one pair of indices. And then I lose one upper index and one lower index. Yeah? So I would do something of this sort. U1 to R1 minus 1. And the last one I call rho. And I sum over this thing. So this would give me now, so the rho is away. Yeah, it's summed away. So this would give me now a tensor which is, I don't know, E, which has one upper index less and one lower index less than the original tensor A. Of course, you could do this over any pair of indices, one upper and one lower. It always gives you something. So the rank loses, in each entry it loses one, right? So that's what is called contraction. So these are the three algebraic operations which can be made with tensors or tensor fields and which will be frequently used. And actually, in particular for the contraction, you see how useful the summation convention is. If you try to write the contraction without index calculus, yeah, if you don't express anything in terms of the components with upper and lower indices, then writing contractions is absolutely awful. So this is one of the reasons why index calculus is really helpful for calculations. And contractions occur very often. So when we deal with Einstein's field equation, we will very often do contractions. Yeah, what else should I mention? I haven't given a name yet for the tensor fields. I should introduce this. Of course, we will use this later often. So we denote the set of all the infinity tensor fields of rank R comma S by, we'll use a curly T. No, R was the other one usually. RS. F. Yeah? So the straight T is a tangent bundle, so that's a set. The elements are tensors, which are situated at a particular point. If I use a curly T, I mean the tensor fields. So these are maps which assign to each foot point a tensor at this point. So that's the difference in the two things. So in particular, we should note that T naught naught M, these are the tensor fields of rank 0, 0. Well, the tensors of rank 0, 0 were just the real numbers, so these are now the functions from M to R. So this is the same thing as the infinity maps from M to R. So this is what you might call the scalar fields, or just the real valued functions. T1 naught is what? There's another word for these things. How do we call the elements in this set? There's one upper, one lower index. You're smiling. Okay, you're not yet accustomed to this whole stuff. So these are the vector fields. Okay, but now everybody should be able to tell me what these are. So these are the vector fields and these are the vector fields, yes. Okay, so the tensor fields of higher rank have no particular names. But actually the totally antisymmetric ones with only lower indices, they have a special name, they are called p-forms. But I will not go into differential form calculus here, so let's stick with this. So I should, here maybe I should, just to make this a little bit clearer. So an element A in TRS of M. What is this? So this can be viewed as a map. Well, if it is a tensor, then it has R entries where I put covectors into, and it has S entries where I put vectors into. But now it's a tensor field, so the foot point is floating over the manifold. So now I feed into the slots not vectors or covectors, but rather vector fields and covector fields. So I can view this as a map from I begin with the covector fields. And then the vector fields. So this is just the Cartesian product. Yeah, so A cross B means the set of all pairs, where the first element is in A, the second is in B. That's a purely set theoretical notion. Don't confuse it with the tensor product. So MyA is a map from this. Well, it gives a scalar at each point, so if the point is floating, it gives me something T naught naught of M. And here I have R factors. Oops. R times. And here I have S factors. So I have an alpha 1, alpha R, x1, xr, and my A eats all these R covector fields and the S. Sorry. Yeah?
There should be S times and R times.
Did I confuse it?
In upper formula.
No, I think it's true. Look, this eats covectors. This eats things with lower index, so it must have an upper index. Yeah? Do I have to? That's an interesting question. Look here. So let's assume we have only one of these dx news here. So my A would have one lower index. What does it mean? On what things operates this? Yeah, let's consider the case where I have only one lower index, O1. Then I have here only one of these terms. And what eats this object? Does it eat vectors or covectors? It eats vectors, right? So it eats things with an upper index. So the tensor has a lower index. But what I put into the slots is something with an upper index. So just the other way around, right? So I think what I've written here is correct. So I want to have an A of this type with R upper indices and S lower indices. So I must feed into the first R indices things which have a lower index. So I must be covectors. And in the remaining S entries, I said things with an upper index, which are vectors. Yeah? So just in order to make the pairing working, that can form sums. Yeah, sums only work over a pair of indices where one index is an upper and the other is a lower. So I think by way of exception, what I've written is correct. But I think this was good that we could clarify this point. I think this was I think that's a problem which many of you might have. So and I now feed this here now into the slots. x1, xs. Okay? And this gives a function. At each point it gives a number, so altogether it gives a function. Makes things a little bit more complicated. You can also read it in a different way. You could, if you like, you could view the same object as something where you leave slots open, and then it maps to some other thing. So that's a remark. And actually that's done quite frequently in practical calculations. Remark. I have to see what names I give to the indices. Now it's a little bit tricky. Oh, I forgot something very important. It's not an arbitrary map. I've just written here can be viewed as a map, but this map must have a particular property, and that's very essential. It must be possible, well, first of all, to use the distributive law. If I feed sums into this, okay, that's rather trivial. But the non-trivial thing is, if I write a function here, it must be possible to take this function out. Because a tensor is linear at each point. So it's not only for real numbers, it's really for functions. That it must be possible to take functions out. So this expression must be multilinear with respect to functions, with respect to coefficients which may vary on U. And that's an important property. And actually when you want to check if something is a tensor field or not, then that's precisely the property you have to check. Anything else is fairly obvious. We will do this, not today, no I will not manage. But tomorrow we will introduce a torsion tensor and the curvature tensor. I will write down the expression, and it will not be quite obvious that they are actually tensor fields, and we have to prove that they are tensor fields. And the way in which we do it is, we will prove that if we take functions out of the argument bracket, that it's allowed to take functions out of the argument bracket, so that they are linear over functions, not just over real numbers. So can be viewed as a map that is linear in each slot with respect to functions. Yeah, if I form linear combinations where the coefficients depend on the foot point with respect to functions on M. So, yeah, it's clear that this property must be true, because a tensor is defined in the way that a tensor would be something of this sort evaluated at one point. If I go to one point, if I evaluate this A at one point, then I can only put covectors and vectors at this point into the slots. And then this linearity must hold, that I can take numbers out. And now I do this on an open subset of the manifold, and then I must do it simultaneously everywhere. And this means that it must be allowed to take functions out. And that's a non-trivial property a tensor field must have. So that was very important, and actually we will use it often in the following. So what I said was, what I actually wanted to say was that the tensor field can be written in this way as a map, but it can also be written in a different way by leaving slots open. So we could view it as a map into another set. Now let me see what the notation is. I have to be a little bit careful. So I have an A in TRSN, let's assume. So we mark A in TRSN can be viewed also in addition to this representation as a map, well, let's call it A hat, which now acts on a certain number of vector fields and covector fields. So let's say my tensor field was of rank Rs. Now let's say I feed only R minus R hat entries into it. So I have here TO1M cross and so on cross TO1M, but I do not have R factors. That would saturate all the slots of my tensor field A. I only feed R minus R hat entries into the slots, and analogously here cross T1OM, here not S but rather S minus A hat times. How do I do this? Well, I have now alpha 1 to alpha R minus R hat and x1 to x S minus S hat. And I want to feed this into A, which has more entries. So I have my A1 to A R minus R hat, but then there are entries left open. It's a certain number. Okay, let me write it this way. Yeah? So if I feed all these things which I have available here into entries in which I can put covectors, then there are still some open because I have R slots, but I have only R minus R hat objects to put into the slots. And the same for the x's. X S minus S hat, and again a few slots remain open. So what I get here is something which is a tensor field. Well, I have now R hat slots open for covectors, and I have S hat slots open for vectors. So I have such an object. And of course, this map A hat is in a one-to-one relation to this map A. It has exactly the same information, right? So we can view tensor fields not only as maps which go into the OO tensor fields. We can view them as maps which go into any other tensor bundle of lower rank, just by leaving slots open. And that's actually something which we do quite frequently. When we introduce a torsion tensor and the curvature tensor, they will be introduced by maps of this sort, where you have here not T naught naught M, but rather T1 naught M or something like that. So that's another identification which makes matter a little bit more complicated, but which is actually a very simple construction. It's just difficult and awkward to write it down. So that's a way in which we can handle tensor fields, and now I have 15 minutes left to talk a little bit about differentiation of tensors. So the next section would be covariant derivative and curvature. Let me just begin with this. Yeah, any questions? Probably lots of questions, right? So I'm well aware that if you see this for the first time, then this is hard stuff. But I will try to give you a feeling of the relevant things, also with the help of the tutorials. So again, I strongly encourage you to do the exercises. So they are, I try to collect them in a way that they are really helpful to understand what we are doing in the lectures. So until now, what we have done was, well, as a mathematician say, this was about natural structures on manifolds. We had defined a manifold, and everything else we constructed was then given. So we could construct vector fields, tensor fields, and so on. We didn't need any additional structure. Now we want to ask ourselves how to differentiate tensor fields. And we will come to the conclusion that it is necessary to introduce an additional structure. Namely, that's what we call a covariant derivative or linear connection. And that's the reason why I give this a new subtitle, because it's now a new structure. So this will be one of two additional structures on manifolds we will introduce. Then in the next section we will introduce pseudo-Riemannian metrics, which of course will be the most important additional mathematical structure for relativity. But we also have to know something about connections. So that's 4.2, I think. No, let me write covariant derivative. Covariant derivative. So that's a certain additional structure which we want to define, and I will explain why it is necessary to introduce an additional structure. And with the help of covariant derivatives, we can then also define what is curvature, which obviously is a very important notion for relativity. So this notion of a covariant derivative comes from the question, how can we differentiate tensor fields? If you start thinking about this question, you will come to the conclusion that you have to introduce some additional structure. On a bare manifold, on a manifold without structure, we cannot differentiate tensor fields in a reasonable way. At least not tensor fields of arbitrary rank. And why is that? So the question we want to ask, how can we differentiate tensor fields? So an obvious idea would be the following. I do it in coordinates. So I represent my tensor field in coordinates, and then I differentiate just the components, in the sense as we have learned to differentiate real valued functions. So that's obviously something which can be done. But let's discuss if this is a reasonable, or in which sense it is a reasonable construction. So an obvious idea would be the following. If I have a tensor field, or let's say, by way of example, let's consider a covector field. Let us consider, by way of example, an alpha of T01. This will be enough to explain why it doesn't work. This means in a chart we have alpha mu dx mu, or if somebody uses another chart, you would have alpha mu twiddle dx mu twiddle. So try to define a derivative of alpha by the following. I just differentiate these components. So I form this quantity. Yeah? So this has two indices. Of course, I must sum away both of them. So I need now something of this sort. So I would write it in this way. So I do it in my chart. And now you do the same thing in your chart. So you would do d sigma twiddle, alpha mu twiddle, dx mu twiddle, dx sigma twiddle. And now ask yourself if this is the same thing. So that would mean, do these things transform like second rank tensor fields? Yeah, that's the same question. Yeah? So if this equality would hold, this would mean that this object would be the coordinate representation of the same tensor field as this here would be as for the other thing. Then I would have one tensor field defined by this expression. I could form this derivative in any coordinate system I like, and I would get a sort of derivative for my alpha. But if you check this, and you will do this in the next worksheet, but the equality does not hold. For arbitrary, for very special coordinate transformation it does hold, but not for arbitrary coordinate changes. And that's what we discuss in the next worksheet. It's number 6 or number 7? The next one, which I distribute at the end of this week.
7.
7 already, okay. So he leaves this for the time being, so we will do this, actually you will do this, you will do the calculation yourself. So you will see that this equality does not hold. So what does this mean? It does mean, of course, I can define the derivative in one coordinate system. Yeah, I just fix the coordinate system defined in this way. Then I get a tensor. But if somebody does it in another coordinate system, he gets a different tensor. So there are two possibilities. Either we would have to live with an object which is not a tensor field, yeah, because it doesn't have the correct transformation behavior, or we would have to live with a theory where particular coordinate systems are distinguished. And we don't want to do either of the two things. And that's the reason why we abandon this notion of derivative. It doesn't make tensor fields into tensor fields. So this derivative, so this sort of derivative, just doing partial derivatives of the components. So this sort of derivative does not map, does not make tensor fields into tensor fields. Yeah? So if you choose a coordinate approach where you just speak of tensor fields only in terms of their components, then you would ask the question, is this a second rank tensor field? A tensor field of rank O2. You would have to check how does it transform under coordinate transformation. Does it transform with the inverse Jacobi matrix in both entries? And you would find it does not. And you say, aha, it's not a tensor field. And that's what I've written here. Yeah? So it does not make tensor fields into tensor fields. So it is a sort of derivative, but it doesn't give us a tensor field as the outcome. And we don't want to have anything like that. We want to have a derivative which makes tensor fields into tensor fields. In order to do this, we need an additional structure. And that's what is called a connection or covariant derivative. Maybe I could just write down the definition and then we discuss it next time. So we need an additional structure on M to define a derivative or differentiation, a process of differentiation. To define a differentiation that makes tensor field into tensor fields. And this is called a covariant derivative or a linear connection, covariant derivative. So it's an additional structure, it's not automatically given on a manifold. It has to be introduced additionally, but if we have one, then we can define covariant derivatives. Then we can differentiate in a covariant way. And the precise definition I will write down next time. So this is this object which is denoted by del, which I think many of you have seen already. So that which allows us to talk about geodesics then, about parallel transport and about curvature. So that will be the program for tomorrow. Okay, see you tomorrow.